Inverse distance weighting is probably one of the most commonly used methods for interpolating a surface. I think that's because it's fairly easy to understand, and it also does a pretty good job of creating a decent surface. So as I said, inverse distance weighting is quite popular. It's a simple way to apply Tobler's law. So essentially the idea is that you're taking existing sample point values and you're weighting them according to how far away they are from the point that you're trying to estimate, which is a really direct way of applying Tobler's law. And I should mention here, I suppose, as well, that it's a local interpolation method, meaning that it's only using sample points that are relatively close to the point that you want to estimate. So if we want to estimate a value for a given point, we're going to do that based on the surrounding sample point values, right? And we're going to weight that based on their distances. So we measure the distances from the point that we want to estimate to the other sample points, and then we're going to convert those distances into weights. Now it's important to point out here that the weights have to add up to 1. If the weights added up to more than 1, then we would end up overestimating our sample value for our location. And if we underestimate it, then we're going to underestimate our calculated value. Sorry, calculated, not sampled. So then we multiply each sample point value by the weight that it has based on its distance, and that will give us the interpolated value. So just to make sure that's clear, so here we have a sample point value of 15. We have a weighting that's based on the distance from that sample point to the point that we're trying to estimate. So we're multiplying our 15 by our weight. Then we're going to do the same thing, multiply 10 here by that weight here, and so on, okay? And so that's essentially, in a nutshell, how inverse distance weighting works. The weighting is inverse to the distance. Okay, so let's keep going. Okay, so we're calling this inverse distance weighting. So how do we define the weights? Or another way of putting this is, how fast should the weights decrease with distance? So the idea here is that we have our diagram from the previous slide showing us that we have weights, and we're applying those to each sample point. And that's what I'm trying to show here with this chart, is that we have distance across the bottom here, and we have the inverse distance values on our y-axis. So at a distance of 1 meter, we have an inverse distance value of 1. In other words, if we have 1 over d, which is what we have in our legend here, 1 over d to the 1, which is basically just 1 over d, then that's, in this particular case, 1 divided by 1, that's going to equal 1. And so our inverse distance weighting on this chart here always ends up starting with 1. So then we can go to 2, and since our inverse distance weighting here is 1 over d, so that's 1 divided by 2, we end up with a value of 0.5. That's the weighting that we're going to apply. And then for 3, it's 1 over 3, so that's about a third, or 0.33. For 4, it's a quarter, so 0.25, and so on. And so you end up with this decrease going through our distance trend line here, so that we get a drop-off that takes place based on the fact that we're using 1 over d. Now we have some options in terms of how we define this inverse distance relationship. What if we decide instead to use 1 over d squared? So what that does, as you can probably see here, is it causes the line to drop off more quickly. So now we're still starting with 1 over 1, because 1 over d to the squared is still 1 over 1. But then here our 2 is now 1 over 2 squared, which is 1 quarter. So that's dropping off much more quickly than 1/2. And so you can see how this continues along here. Now, this is a deterministic method. In other words, we're making an assumption about which is the right one to use and how much our particular phenomenon drops off over time. So if it's zinc concentrations with distance from a river, or air pollution concentrations with distance from a smokestack, we need to make an assumption about how much we think that drop off is going to occur and how we're going to model that with our weighting. Here's the line for 1 over d to the third, or d cubed. So same thing again, as we're going from 1 over d to d squared to d cubed. So we're getting a much steeper drop off over the same distance for the thing that we're trying to estimate. And just to make sure this is clear, what these curved lines are showing is not the actual, say, zinc values. It's showing the weighting that will be applied to the zinc values based on distance, okay? So here we have a weighting of 0.5, here is 0.25, and here is 0.13. Okay, so if we go back to our idea of trying to estimate a value, we have our sample points with their zinc values in this case. So here's our zinc concentrations in parts per million. Here are our distance values, so 4 meters away, 2 meters away, and so on. And here's our 1/d weighting values. So if we have a distance of 4 meters here, 1/4 is 0.25. If we have a distance of 2 meters, 1/2 is 0.5. So that's how we're calculating the weightings. But you'll notice that the weightings don't add up to 1, they add up to 1.28 in this case. So we need to somehow standardize those weightings to make sure that they add up to 1, so we're not over or underestimating our zinc values. So to do that, what we do is we take each of these values, so which is 1/d, so here let's say 0.25, and we divide it by the sum of all of the values. So we're adding up all of these together, all of these together to get 1.28, and we're dividing each one of these here, 1/d, by the sum of all 1/d's. So it's just a way of kind of standardizing the values so that they add up to 1. And so when we do that, we end up with these weightings here that have been standardized. So a distance of 1/d, which is 0.25, becomes a weighting of 0.19, 0.39, and so on. And like I said, the important thing here is that all of the weights together add up to 1. So each weighted value is then multiplied by, so we have the value multiplied by the weight, and so we end up with a weighted value. So we have our 15 multiplied by a weight of 0.19, and that gives us a value of 2.9. So that's the weighted value that's going to be used for our calculation. So then our interpolated value, so the whole point here is that we're trying to figure out what that value should be. We add up all of the weighted values here, that gives us a value of 11.1, and that's our estimated value, or calculated using our inverse distance weighting for that location. When you use the inverse distance weighting method, there's an artifact that sometimes becomes apparent known as the bullseye effect. And if you've been following along and thinking about how the 1/d or 1/d squared works and how we have these drop-offs taking effect and how we're having weightings according to distance, you can see how this might happen. And essentially what this means is that we have one value here that's sort of overemphasizing or having more of an influence on the immediate area around it than it probably should be. So if we look at this in 3 dimensions, you can see here this bullseye effect. And if I zoom in here, it becomes more apparent. So it's a bullseye, of course, when you're looking at it from above, but here it looks a little more like a mound, let's say. And so the idea is that we don't have any other sample points that are nearby. Like there's one over here, there's one over here, I think there's one there. And since we have this inverse distance weighting effect taking place, there's no other value nearby that's contributing very much to the weighting. So the idea here, remember, is we're not estimating the value for the sample point itself, we're estimating a value for something nearby like that. And so when that calculation is being done, this is getting a really high weighting because it's really close. This is getting a low weighting because it's much farther away, and so is this, and so is this. And so you end up with these really low weightings for farther values and one high weighting for one close value for, and this is happening for all of the cells that are nearby. And so you end up with this bullseye effect or this kind of mounding that takes place because of it. By the way, this also happens in reverse. If you have a really low value, I guess we could call that like a dimple or something like that. And so this is just a way of kind of putting all of this together, is we have our bullseye here, which would be something where we have a high weighting somewhere nearby. And so that would be this sample point here, and then much lower weightings for sample points that are farther away. Okay, so that's just generally how it works. I don't want to over-explain this, but it's just something that's an artifact of inverse distance weighting. There's not necessarily a lot you can do about it, but it's something to be aware of. I wanted to explain something about using different units with inverse distance weighting and whether this does or does not have an effect on our weightings. So you may think when you look at this to begin with that we have a problem. And why is that? What we have here is distances from 0 to 10 meters. And here we have distances from 0 to 10 meters, but it's being specified as decimeters, okay? So these are the same distances that so 1 meter is 10 decimeters, 2 meters is 20 decimeters, right? So they're the same distances, but we're getting a very different curve with those different units. So you would think this would be a problem, is that we're looking at this and going, well, wait a minute, this isn't really working very well because we're getting two different weighting functions based on the same distances. It's actually not a problem, and I will show you why. So here we have a curve based on our distances specified in meters. Okay, we have a scale from 0 to 1. Here we have the same distances, only in decimeters, with a scale from 0 to 1. So this is where it makes it look like we have a problem. However, if we use a scale from 0 to 0.1, we end up with exactly the same relationship with the two of them, right? So in other words, if we scale it, we have the same curve, the same weightings. Well, that's actually what's happening when we do our calculation and divide by the total sum weighting here, okay? In other words, it all comes out in the wash. They're still being standardized to the same relative weightings, even though we're using different units. So I wanted to kind of point that out because it's actually one of the beauties of it is that it doesn't matter what units you're using, it will still work. And this is just a way of showing this mathematically, is that we have, for example, here are two different distance weightings. So they're both 1 over d, but one's in meters and one's in decimeters. And so you think that's a problem, but once we actually calculate the weights here, the weightings still end up being the same. Okay, so everything works out okay. Just wanted to point that out because it is something that's a useful kind of feature of using IDW, as it's called. So here's a comparison of 4 different surfaces created from the same starting sample points, but using different weightings. So we have 1 over d, 1 over d squared, 1 over d cubed, 1 over d to the 4th. And as you can imagine, with 1 over d, we're getting a more gentle change in slope from the river to areas with increasing distance from the river. And as we increase our weighting that's closer, so 1 over d squared, you'll notice that as we're comparing these gradients across here, that we have a more steep drop-off here and a more gentle drop-off over here, which is what you would expect to see based on the fact that we have a different kind of function. So here we have a more gentle function in terms of 1 over d, and here we have a more steep drop-off with this particular function. So this is just a comparison of the same zinc value with the same distances, but getting different weightings from that. So the weighted value with 1 over d is 3.9, but when you go to 1 over d cubed, that weighting is 6.7. So it's the same point at the same distance, but because we're changing the weightings, you think of it this way, is that because we're getting that drop-off, the points that are closer are getting more of a share of that total weight. Remember, the weights have to add up to 1, so the ones that are farther away are getting even less of a share and are being minimized, whereas the ones that are closer are being exaggerated more or getting higher weightings. One thing to note with inverse distance weighting is that it's an exact interpolator. And why is that? Well, it's because if you have a distance of 0, so in other words, if you're trying to estimate a value at a location where there already is a sample point, then the distance from the sample point to the estimated location is 0. And when you try to do a weighting for that, you're going to get 1 over 0, which is undefined. And so since it's undefined, the sample point value is substituted for the undefined value. So they basically kind of just say, well, then in that case, we'll just use the actual sample value. So in that way, the sample in your new surface that's created, the sample value is going to be exactly the same as the estimated value because it is the same. You've actually substituted it, so that's why it would be considered an exact interpolator. So how does the software go about deciding which points to use for each inverse distance weighting calculation? Well, there's 2 ways that you as a user can specify this. You can either say that it will use all of the points that are within a certain distance, or you can say that it's going to use a certain number of points regardless of distance. So you can use a fixed search radius where you say, at this set distance, use all of the points that are within that radius. So it's using all points inside that distance. Or you can use a variable search radius where it's going to say you have to use whatever 1, 2, 3, 4, 5, 6, 7 points, no matter how far away those points are. And you can see that both of those can be slightly problematic. So what if you have no points that are within a certain distance, or what if you have, if you set it to having 7 points, but one of those points is really far away, is that such a good thing? Although actually if it's far away, then the distance weighting will be low, so maybe it doesn't matter. Okay, so those are the two ways you can specify it. So if we look at our zinc sample points and say, well, how would we decide what that search radius should be? If we say we're going to use all of the points within a certain distance, is there some way that we can kind of use some empirical data to decide what that search radius should be? Well, yeah. So what I decided to do was use the near function to calculate the distance from one point to its nearest neighbor. All right. And if you do that for each of the points, you end up with a distance value for every single sample point. So what this near distance field is showing us is what's the distance from, in this case, this sample point here to the next nearest sample point. And in this case, that distance is 90 meters. So how does that help us? Well, what if we just then took the average of all of those near distances? So in other words, this is the average of how far away any 2 points are from each other. That gives us a value of 106.7 meters. And so if I create a buffer of 107 meters just to visualize what this would look like, this gives me an idea of how I might be able to base my search radius for my inverse distance weighting on something real. So this is what I did, is I said, okay, well then, if we use this, then at least I know that if I set it to 107 or more, then I'm going to capture at least a few points around every location. One thing to keep in mind with inverse distance weighting is that it has this kind of unfortunate thing that it can underestimate or overestimate points at certain locations. And let's see why that might be. Let's look at a profile of a landscape here and treat this as though it's reality. So this is what we're trying to construct as a surface based on sample points. So here's our sample points that's going to be used by the inverse distance weighting tool, okay, to estimate what this reality really looks like. So the problem with inverse distance weighting is that the weightings are based on an average. And you say, okay, so the problem is that the result of the estimation for a location is based on something that's multiplied by an average, or that's using an average. And what that means is that the result can only be within the range of the lowest value to the highest value, okay? So if you think of it this way, if I had a group of people in a room and I said, give me all of your ages, and then I'll take the average of those ages, and let's say that people are aged between 10 and 30, so then the average, let's say, is somewhere around 20, right? So you can't have an average that's 50 because there's nobody in there that has that value. You can't have an average of 100. The average for that range of values has to be inside the range. It has to be somewhere between the lowest value and the highest value. And this is what happens with inverse distance weighting, is you end up getting a result that looks like this, is that you're estimating values here that have to be inside the total range of values being used for the weighting. And the same thing up here is that you can't have something like this because this can't exist when you're using the weightings. So when you estimate or you calculate a value for inverse distance weighting, the calculation is actually going to pull that value up, and it's going to overestimate what that value is. The actual value, the terrain, is down here, but it's being pulled this way because it has to be inside that range of the sample values, so I'm going to end up with an overestimate. Same thing with the top of the mountain, is that that's going to get pulled down to be inside the range of our weightings, and I'm going to get an underestimate from that. And so again, this is just something to be aware of. It doesn't mean you should never use IDW. It just means that you have to know that when you're looking at your results, you may end up with values that are over or underestimating. So this is a way of visualizing this as well. And you can see that the values that are being calculated for any point on our study area have to be inside the total range of values. And in fact, it's not even that. It's inside the range of values being used for the sample, which might be just what's locally nearby. So if we take this DEM as though it's reality, which it's not, but it's, it's close to it, it's a pretty good estimation probably, then we can compare that to the surface that I calculated using my inverse distance weighting. And I just add this in because it's a nice way of being able to kind of see how some raster analysis works and some error checking kind of things. Is what I can do is subtract my inverse distance weighting surface from the DEM to see if there's a difference between the two, and where there are differences, are they overestimating or underestimating our values? And so this is what we end up with. So I've just color-coded this according to the same colors I showed in the previous diagram. So our overestimates are shown in magenta here, and the underestimates are in purple. And you can see, sure enough, that there are lots of places across my study area where we are getting these artifacts taking place based on the fact that I'm using IDW. So here's the DEM, the IDW, and the difference. It's just a way of showing them all together, just so it's more clear what we're actually seeing. So one way to visualize this even further is to look at a profile across the landscape. So we'll look at this line across here, and across here, and across here for the three different versions of this, DEM, IDW, and the difference. So I've just drawn this profile here, and you can see that we have our differences. So the DEM, what we're treating as reality or close to it, is in gray, and the IDW version is in red. And here's our profile from A to B. And so what's happening here is that we have an overestimate taking place across this part here, which is what's happening here. So the estimated value that's being calculated is much higher than reality, therefore it's an overestimate. Here, as it gets to this part, the estimated value is lower than the DEM, or what we're treating as reality, so this is an underestimate. So this is just another way of trying to think about this. I always try to encourage people to really dig deep into these concepts and these methods to make sure that they understand them and that they have different approaches or perspectives on what works and why does it work and what kind of problems might there be with it, so that when you actually go to use it, you have a really good, strong understanding of what it's doing, why it's doing it that way, and what the limitations are.